Have you ever picked up a rock and asked yourself, I wonder how far I can throw it? Today's subject is the optimal launch angle problem, but let's not get too ahead of ourselves. In the world of physics, one of the most important objects is the vector. To put it simply, a vector is an arrow that indicates the magnitude, called module, and a direction that is specified by the tip of the arrow. We use these vectors to indicate quantities that cannot be fully described by using a simple number. One such example are forces. Newton's second law states that a force equals a mass times its acceleration. One example of such a force is the force of gravity. Here's a breakdown of its terms. The minus sign indicates that the force is attractive, meaning that the vector related to the force will always point toward the mass that's creating it. This force can also be connected to Newton's third law, written on the right. One important note is that these two forces have equal magnitude, meaning that no matter the relative mass of the objects, both of them will feel the same force. Let's focus now on the acceleration that each body would have. As we can see, its acceleration depends on the other's body mass, and not its own. This means that in the case of a projectile, compared to the planet Earth, the accelerations will be completely different. Needless to say that the Earth, for our studies, doesn't really move compared to the bullet. Starting from the value of the gravitational acceleration, which we now consider constant, we observe that the acceleration is the second derivative of the position with respect to time. This means that by following the simple integration rule stated here, we can obtain the law of motion of a projectile. It is in this context that we introduce the problem of the optimal launch angle. Or to put it more simply, how far can I throw an object given the assumptions cited here? We will start by looking at the ground level case. From the equation we obtained earlier, we put the correct values as cited in the problem, namely the acceleration g, the initial velocity along the y-axis, and their starting height, namely y0. Here, we also introduce another equation. This equation is for the motion of the object along the x-axis. This time, there is no acceleration and only the initial speed v0x. If you're familiar with throwing objects, you will know that no matter how strong you are, you're always bound to produce a parabolic trajectory. But why? The answer lies in the equations we wrote. The first thing we do is that we find t as a function of the x position. Then, substitute it in the y equation from earlier. This will give us an equation that, from a mathematical standpoint, represents exactly a parabolic shape. We can further improve this formula by using some trigonometry. Our objective was to study the ground level case. Hence, we write the two following conditions. When applied, this is the result that we get. By grouping the x value, we can now obtain two different solutions. The one that interests us is only the second one. Simplifying it further yields the following results. This equation shows that, in the ground level case, two quantities are fundamental: the initial speed and the angle. In this case, since the sine is a periodic function, its maximum value is 1, and we obtain it by putting theta as 45 degrees. This is a visual representation of such motion. For the case of the above ground level projectile, we start the same way we did earlier. Only this time we add the condition that the initial height is different from 0. The equation we obtained can be solved by using the quadratic formula. The result may seem quite confusing at first. Here, I tried to be as clear as possible by guiding you through each step. Feel free to pause the video if you're interested in the calculations. The result we obtain tells us the distance of the projectile if we have an initial velocity, angle, and also initial height. Here's what this motion looks like. To get a better understanding of this formula, let's put it in a graph. By placing the theta angle along the x-axis and the distance along the y-axis, we can obtain the following graphs. This is done by choosing different heights. Since our objective is to produce the greatest possible distance, we look for the maximal points in the graph. By running some simulations of the different trajectories, we can obtain these tables that show the correlation between angle, initial speed, and height. But can we do better? The problem of finding the maximum value of a function is, in the mathematics world, quite an unknown one. The first thing we need to do is to derive the formula we got with respect to the angle and equal it to 0. This derivation is quite complicated. On the screen, I displayed as much as possible of the steps. The steps use trigonometry formulas to transform the various sins in cosines, and some simplifications. And here we have it, the optimal launch angle formula for a projectile above ground level. As we can see, the only two values that are important are the initial speed and height. We can visualize this formula by putting the angle in function of the height, and select the speed of 5 meters per second. These are the optimal launch angles at different heights. If you enjoyed the video, subscribing helps me out a lot. Also, if you have any feedback or if you have any questions, feel free to leave a comment and I'll make sure to reply to them. Thanks for watching.